Right, we're ready to go. Okay, here we go. I want to have a look today at kinetic energy and elastic energy stores. So what I've got is a couple of setups and I want to have a look at it. We a little bit later this morning because of little Bluetooth problems with the Pasco equipment in that it didn't. So we're working the other way around. You'll see the equipment as we set it up in a minute. So what are we going to have a look at? Well, let's take a look at the basic design. What we've got is a clamp, some Hot Wheels track, and down here I've got a light gate. Now, what we need to do is we need to have a look at putting a little vehicle up here. We're going to place this exactly 1 meter from the top, and what we'll do is we'll use this idea that gravitational potential energy equals mgh. So that means we'll need to take the mass of the car, we need to know gravity and height so we can work out what we are. Now, I've previously weighed the car and it weighs 34 grams. So we've got 34 grams, that's got to be turned into kilograms. So there are 1,000 grams in a kilogram. So we've got 0.034 kilograms. We're going to multiply that by gravity, which we know to be 9.8, and we're going to multiply that by 1. So I've got my calculator ready to go. So I'm going to simply put in 0.034 times 9.8 times 1, which is irrelevant, and that's going to give me about 0.3332. So that equals my gravitational potential energy. We're going to now let the car go, and as it goes down, it's going to change its gravitational potential energy, and that's going to turn into kinetic energy. When it gets down to the bottom, and I've put a light gate where it's just about got horizontal, we're going to measure the distance it's going to travel. Now, for kinetic energy, we need to know something about the velocity. So we know that kinetic energy equals 1/2 mv squared. Zoom in a little bit for you. Now, if I know that we've got this k is 1/2 mv squared, what I can do is I can calculate here the velocity. The velocity equals the distance, and they use the letter s here, over time. Well, if I know the distance, and if we have a look at this light gate, what it consists of are 2 beams of light coming out. The car goes through the first beam, and that starts the clock, and it goes then through the second beam, and that stops the clock. We know the distance between these 2 dots, and we can measure the time, and so we can work out what the velocity is. Well, that's the theory. So once we then know what the velocity is, we can calculate what the kinetic energy is. And that's going to be a half times the mass, which is going to be 0.034 of a kilogram, times our velocity, which we're going to work out, squared. And what we should find is that our gravitational potential energy will equal our kinetic energy, because this is called the law of the conservation oh dear of energy. I said it'd been a bad time trying to get all the equipment set up. It's one of those days when it didn't work. Right, so we're going to move over and have a look at the equipment. And what we're going to do is we're going to go on to a different camera, which we're just now setting up. This is all the vagaries of trying to do anything live. And we're going to try and see what happens. So there we've got the setup. So I have got here, I've got a car, and we've got this track. So just a few technical hitches. Right, we've got the car, we've got the track. The car is going to come down. It's going to go through this light gate. So this light gate here has two little sensors. I'll bring it closer to the camera for you. It's got two little sensors. You can just about make out two lines, and there are infrared beams here which are going to be cut. So I'm just going to place that, and I'm going to try and place this such that it's level, and that the car, when it goes through, you might just see an LED light come on. There's an LED here that registers when it goes through. Okay, so this is what the experiment is going to look like, and what we're going to do is try and have a go at it. Right, that's the camera set up. This light gate is connected by, well, it should have been by Bluetooth, but the system not working, hence the reason for being late today. And what we're going to do is we're going to take this car, and previously I've set up a meter rule, and I'm going to try and get this car to go down this track like so. So we do have a little technical problem. So what I'm going to do is I'm just going to try and lengthen the track a little bit. And we'll see if that works a little bit better. There we go. I'm going to have to move the light gate just down a little bit further. We'll get it set up again. Let's see if it works. Yep. And we're ready to try and do the experiment. I've got to make this fairly loose as a as a sort of thing to go down, because otherwise the car, as you can see, falls off. Right, let's get the software set up. Now, what I've got here is some special software. This is made by a company called Pasco, and it's a thing called Capstone. Let's have a look. We've got the right one. Right, here we go. Let's just move that out of the way. And I'm going to bring up the Capstone software. Right, what I have done is I've set the hardware up, and we've got here a USB connection to the smart gate, and I've set the smart gate up to record the velocity between the gates. Now I'm going to stop everything, and we're going to have a go at doing a new one of these. So let's start recording, and we're going to see what happens. Now, when we release the car, we will probably see this is going to be negative because I've got the gate round the other way. So let's go and have a look and see what's going to happen. I'm going to set this going, which it is. We are now going to see what's going to happen. 3, 2, 1, go. And if we have a look at our numbers, I've got some rather interesting ones because I've got several numbers there. Didn't expect that. I know what's causing the problem. That gave me just 1. So what our problem is very simple. The gate is bouncing. So I'm going to bring it just a bit further along. The other problem I'm going to get is that the car may lock up. It may come back and bounce through. So we'll try again. 3, 2, 1, go. And let's see what readings we got. Yeah, I got 1. So that's looking okay. So we've got it all set up now. So let's try for real. I've got my patented car stop. I suggest we all use towels at the end of roads to try and stop cars. 1 meter, 3, 2, 1, go. And we got here a speed of 2.89. I'm not convinced that was right. We're going to do this a few times. So we're set up now to have another go. Right, 3, 2, 1, go. That also didn't go right. My release is failing. That's a good one. And that gave us, I don't know, that's still making a mess. Right. How boring. Right, we'll try again. This is what real science is like. When you see one of my videos where we've done this, we can make sure it all works properly. When we do things live, then things don't work quite to plan. 3, 2, 1, go. That was a good run. And again, we've got various things. It should be about 3.73. That's what I'm expecting to see. Let's have another go. Still obviously getting a little bit of bounce here. I can perhaps improve this. We'll go to a slight improvement on the track. This is the Mark II version. Right, Mark II version, we're going to hold the track down with an extra piece of blue tack. Let's see if this goes better. 3, 2, 1, go. And I got the 3.85. Let's have a go at this again. Three, two, one, go. Your camera went off. And that's 377. Right, is camera back on? Just record. That's what I'm doing. What? I'm doing. You're doing. Okay. Just wanted to get about 10 readings to give me an idea. 3, 2, 1, go. And there we've got 3.83. And we'll do it once more. There we go. Right. Okay. So I've repeated the experiment a few times, and it's looking very much like I'm getting a reading of about 3.83. We've got 3.85, 3.77, 3.83, 3.83. So it's about that. So let's take our velocity. So we've got 3.83. Right, so let's go for 3.83 meters per second, and that one number is going to be squared. Right, let's have a look and see what's going to happen. So if we turn the calculator on, then we've got a half 0.5 times 0.034 times 3.83 squared. And that's going to give us 0.249. So let's see what we have. We have gravitational potential energy, which is 0.3332. and that equals 0.249. Well, that's not too bad, really, within the realms of experimental accuracy that we've got, except something obviously is happening. Now, what's going wrong? These numbers should be exactly the same, and they're not. Let's give you a clue. We'll do the experiment once more time and listen carefully. We'll set it up. Ready to go. Listen. I can hear the sound of the vehicle. So something's going on here, isn't it? So this was here going to be gravitational potential energy, and that's going to give us kinetic energy, true, but it's also going to give us some sound energy. Plus, it probably is going to give us a little bit of heat, and this is in the form of friction. When we look at the wheels on the car, we'll probably find that temperature has gone up very, very, very slightly. So my gravitational potential energy does equal my kinetic energy if we could measure perhaps the sound energy as well. Now that's quite difficult to measure because the sound energy you heard this little car, and it sent out some sound energy which we picked up with the microphone. But in fact, the sound energy was going in all directions. So we've got very little idea about how much sound energy there is. I can guess it's probably the difference between this and this. So there we have the first of the two experiments I want to have a look at today. The second experiment I want to have a look at is that of something called Hooke's law. Now, many people do Hooke's law, and they do that in about year 7, but in fact it comes into the GCSE syllabus, and it's an experiment you're expected to know. So I'm just going to set that up, and we'll have a look at Hooke's law very, very quickly. Now, my Hooke's law experiment looks like this one here. Let's have a look, and Paul's just adjusting the camera. Are you ready? No. Right, and we'll get that set up. Right, camera is set up, and I don't need this track anymore. So what I'm just going to do is take it out of the way. And that's going to leave us with this setup for Hooke's law. Just disconnected the wire so I don't break my neck. Right, okay, so Hooke's law. What we've got set up is a spring. We've got a ruler. The spring's got a little arm on it to try and point to a point on the ruler. And what I've done to try and improve the experiment is I put a mirror behind the ruler. Now, what this enables me to do is that as I add the weights and we have a look at what's happening, this arm we can check to see if it's correct by looking at the number, this line, the number, and the number in the mirror. And when they're all lined up, we've got no problem. So let's start this little experiment. And what I'm going to do is I'm going to start with just a couple of weights on here to start. So I've got just 10 grams for a hanger. And I'm going to set the mirror up so it's behind there. And Paul's going to try and get the camera at the right height. And I'm going to try and adjust this so you can see perhaps a little bit better. And there we have it. So I've stopped it moving, and we can see that this is about, we're going to choose where we're going to do on the line. I'm going to say that's going to be about 11.5. So we're going to now record this information. So let's set this up. So I've got a brief table. We've got here the mass, and it's 10 grams. And I've got here its distance, where we are on the ruler. Let's measure where we are on the ruler. So that's our ruler. And what I want here to record is the extension. So the ruler, where are we? We said it's going to be 11.5, and I'm going to give that an extension of 0. Let's see what happens. So I'm now going to put 10 grams on here. And hopefully we can get the thing lined up. And if I read that one here, I think that is about 11.8, 11.9. Let's say 11.9. So this represents 20 grams. The ruler is set at 11.9, and that's an extension of 0.4 centimeters. We'll do a few more readings. Let's now put on 30 grams. There we are, looks fairly stable. Let's have a look on there. And that seems to be round about 13. We'll call it 13. So this is now going to be 13. And that's going to give me an extension of 1.5 centimeters. Let's look at 40 grams. trying to get it as still as possible. And let's have a look and see. About 14.3.
I'm reminding you, take a Puritan tablets.
Typical machines helping me. And so if we now work out what we've got an extra here, 1.3 centimeters. So that's going to give me 2.8. We'll look at 50 grams. My mirror probably needs just to be moved down a little bit. Hopefully that's lined up for you to see. And Paul's going to bring the camera down very fractionally. Little bit more, tiny little bit more, tiny bit. That's about it. Brilliant. And we can see on the screen that the line behind's now lining up nicely. And I think we're on about 15.7. So our extension here is going to be simply 15.7 minus our 11.5. So we've got there 4.2. And it's probably worth just doing one more here. So let's just look at one more. And we'll have a look at the readings. And I'm looking at about 17.2. We really need to move the camera down a fraction, but we'll not worry about that too much. So I've got 17.2. And if we take those away, we work out it's 5.7. So what's left to do? Well, we've got to try and see what happens when we plot this. And what I'm going to do is I'm going to try and plot this on a graph. Go the wrong way as usual. Right, okay, so let's see about trying to draw a graph. Now, my numbers that we're going to plot along the bottom is the independent variable, the numbers that we are changing, and the extension. Sorry, I got my cameras in the wrong place. And the extension is the dependent variable, which will go along the vertical axis. So I've only got to go up to about 5.7. So if we make a simple graph, we're going to set our mass at 10, 20, 30, 40, 50, 60. Now, these are in grams. Really, this ought to be measured in kilograms. So it's going to be 0.1, 0.2, 0.3. And then our extension, 0, 1, 2, 3, 4, 5, and 6. So when we had 0, it should be, that should be 0 grams. That's just really enough to hold my spring taut. So we are going to pretend that's going to be our point of origin because of technical problems. Right, 20 is 0.4, so 0.5, 0.4 down about there. And then we've got 30, which is 1.5. So I've got a curve, not what I'm expecting. 40 is 2.8. 50 is 4.2. And 60 is 5.7, probably about there. Now, if I ignore my first couple of points, which are probably because I've got my spring being really basically set up, and I'm just getting the tension set up on those. So I would expect those not to be correct. We have managed to achieve a straight line. And this tells us that elastic potential energy, E PE, equals half the spring constant times the extension squared. Now we can work out our extension, we can square it, and so we can work out what our elastic potential energy is. So let's see if we can actually do that. If I take some of these numbers, and we seem to think from our graph that 30 is okay, and we'll look at 50. So we've got our spring constant, which is our elastic potential energy, equals a half times my spring constant, which I have no idea what it is, times the extension squared. And my extension squared is going to be 1.5 squared. Now, do I know what my elastic potential energy is? Well, it's to do with this mass. Turn it into kilograms, that's going to be 0.3 kilograms. Yeah, 30 grams, 0.3 kilograms, just checking with myself to see if that was right, times the force of gravity, and we know that's going to be 9.8 meters per second. So I've got 0.3 times my 9.8. That's going to give me 2.94. And that's going to equal a half times my spring constant times 1.5 squared. Let's rearrange that. So that's going to give me 2.94. Let's now multiply that by 2, and we're going to divide by 1.5 squared, and that should give me my spring constant. Don't know why I did SP. Right, my spring constant. Right, let's do that. So I've got my 2.94 times by 2, and I'm going to divide by 1.5 squared. That's going to give me my spring constant of 2.61. Let's do this again with another set of figures and see if we get the same answer. My 50 grams is going to be 0.5 times 9.8. We're going to multiply that by 2, and we're going to divide this time by 4.2 squared. Let's do that. 0.5 times 2, I mean, it's going to be easy. We're just going to have my 9.8 here, and I'm simply going to divide that by 4.2 all squared, and I've got a number of 0.555556. And as you can see, my spring constant is absolutely nowhere near the same. Perhaps I need to be a little bit more accurate in my experiment as I try and do this. Well, it's been a bit tortuous here trying to get some of this done, getting things set up and organized, but that's the vagaries of doing science. So hopefully that's given you an idea about gravitational energy turned into kinetic energy, and it's given you some idea about a revision of Hooke's law, an experiment you probably did many years ago, and those will turn up normally in the examination. I'll see you again next week. Take care. Bye-bye.